I'm Jiajun. I'm a very new assistant professor of computer science at Stanford. Actually, I just started on July the 1st, so a month ago. I'm happy to present my work on learning to see the physical world. So we live in the physical world. As humans, we really effortlessly see, navigate, and interact with the physical world. So as AI researchers, we like to build machines that have the same capacity. And to do this, let's first review what we can do as humans, but in particular in the context of a popular game that's the game of Jenga. And interestingly, not only adults can play the game, but even young kids can do it pretty well. So look at this video. This is a boy playing the game of Jenga. And he's actually only 3-year-old, but as we can see from the video, the 3-year-old can play the game of Jenga pretty well. He's able to, pick up the block, see the blocks, pick up the blocks, and interact with them, put it on top of the tower, and accomplish what the game requires. And this is a 1.5-year-old play the game of Jenga. So she's younger, so she's not really doing it independently, but under the guidance of her father, following the instructions of her father, she's able to do it pretty well as well. And then she's very happy. And this is a 6-month-old playing the game of Jenga. So looking at this 6-month-old, apparently she has a different notion of playing. So, but though with a different definition, she can actually still interact with the blocks. Right? It's pretty amazing to see this 6-month-old seeing all the blocks, touching them, interacting with them. And our ability to see objects and interact with them is not only limited to blocks, but also applies to new objects. Right? We have now, you can see many fancy toys here. They have different colors, shapes, materials, and textures. And some of them you might not have ever seen them before. Same for the babies, but the baby can also interact with these objects. So my research is about building these what we call the infant machines. How can we really accomplish part of what infants can do? That is, for any new objects, including many that we've never seen before, can we see its shape and physics? Can we predict how it behaves if we interact with it? And really to build a robotic system that interacts with it. So how to do that? Of course, we're going to leverage what has been achieved very impressive progress in the past years. That's deep networks. So this is what you can typically see a deep networks can do. On one hand, they can do really well in seeing, segmenting cars, recognizing them, segmenting them. But on the other hand, they are also very limited because everything you can see here requires a huge amount of training data. You have to annotate a lot of cars and trees, and so to make the system perform well. And on the other hand, they're not really generalizing to any objects that they have not seen during training. Right? Everything you see here, cars, trees, you see a lot of them during training. So this kind of approach is what we call this data-driven approach, right? So you can go from images to predict semantic categories. You can say, let's extend it to also predict object physics, actions, concepts. So learning everything from data. And as we said, on one hand, you're enabled by data because deep networks really do very well in pattern recognition from data. On the other hand, you are limited by data because there are a lot of things like 3D objects and physics which are very hard to annotate. And if you cannot really annotate them, how are you able to learn them? So an alternative approach is what we call this modeling approach. We live in this physical world, and there's actually an underlying physical model behind it. We see there's an image, and what we are really seeing from the image, the reason that we can see this image is because there are underlying world state, which includes a number of objects. Their intrinsics like geometry, appearance, and materials. Their extrinsics, the positions and velocities, and the scene descriptions like lightings and camera parameters. And the process of taking these states and parameters and generates the picture is called rendering. It's an important subject in computer graphics. And you can do that for not only the first frame, but do it for many frames. And across the states, there is dynamics. Given the current state and an action, what's going to happen in the future? And here, in this example, you can see the action as gravity. And this provides a physical model that explains what we're seeing in the physical world. Now, this kind of top-down physical models are actually very powerful. Here I'm showing an example where it's generated by physics engines and graphics engines. It's a movie called Sintel. And it's generated by the Blender Foundation back in 2010 before deep learning. And they generated it because they want to demonstrate how powerful similar graphics engines and physics engines can be. Right? Back in 2010, you can already get very realistic videos like this. And there's no learning involved at all. So now the question is, can we actually leverage these graphics models and dynamics models, or the models, and see, maybe this suggests an alternative approach of building an AI system. So on one hand, these models are very powerful, as we said. They don't really require any trainings. You can generalize to any new objects as long as you give them the cat models and specify the scene states. On the other hand, they're also limited because the fact that you're given these models, you're told how I can render an object, how I may produce their physics, doesn't allow you to do inference, right? So if I'm now interested in an inverse problem, if I'm seeing a video, I want to infer the geometry and physics of the object, then it's unclear how we may inverse these top-down generative models. And also, every model is an approximation of the real world. So there are cases where these models are not accurate. There are cases where these models, for example, they're mostly stochastic, they're mostly deterministic, and they don't really capture the stochasticity of the world. So there are also, this kind of model everything approach is also limited by what models can offer. So the philosophy behind my research is to think about this hybrid approach, where can we integrate learning and modeling so that we can get the power of both the data and the model. And in particular, we think about learning in two ways. The first is learning to inverse. Right? When we're giving the top-down simulation engines, given the geometry and physical properties, we can do synthesis. But can we invert the geometry and physical properties of the objects from raw visual input by inverting a simulation engine? And the second is, can we learn to augment them? As we said, the dynamics models and graphics models, they can be not accurate enough, they can be not stochastic. Can we use learning to augment them? So that hopefully we can get the power or the advantages of both the data and the model. And the key principles behind my research is about building the physical models for the physical world and learn whatever the model doesn't give us. Okay, so let's start by looking at a concrete example of how learning to invert can enable us to do inverse graphics. So let's look at a very classic problem, that is, if we have a 2D image, can we invert and infer what's the 3D geometry of the object in the image. Right? So the process of going from 3D to 2D is graphics, is rendering. And here we care about inversion problem. Can we get a 3D geometry from a 2D image? So if we want to learn to invert this physical model, graphics engines, let's first look at what is the physical model here. We have a 3D shape. And the fact that we're seeing this image, what we're essentially seeing about the 3D shape from the image is the 3D shape you can see as in the 3D space. And there's a light source. The light source sends out rays and hits on the object and get reflected into the camera. In front of the camera, there is an image plane. And so what you're essentially seeing about the 3D shape from the 2D image is not the full 3D geometry. For example, in this example, you're seeing a chair, but only the 3 legs of the chair. Right? You're essentially seeing the visible surface of the chair, not the 4th leg, which is occluded. And the fact that this chair must have 4 legs, or is very likely to have 4 legs, is because you have this prior knowledge that we know and we have seen from our life that chairs mostly have 4 legs and they have to be stable. So, but you're essentially seeing, what you're essentially seeing about the geometry of the object from the picture is just the visible surface. So now we say, if we want to build an inversion system, then maybe instead of building an end-to-end deep neural networks that take it to the image and output a 3D shape, maybe we can do the shape estimation problem in 2 steps as well. The first step is to estimate the visible surface. Here we can say it's depth estimation, because you can see that the depth map showing here is, you can see as a reparameterization of the visible surface. And the second step is, can we go from the depth map and the visible surface to reconstruct the full geometry? Here there's nothing to do with the input image, because the input image doesn't tell me there were 4 legs of the chair. But I want to learn to do that, learn to complete the shape using my prior knowledge and learning from data. So motivated by this kind of inversion approach, we designed a system that has 2 stages. The first is to estimate depth, the second is to complete the shape. And this system, which has 2 small neural networks and the intermediate representation depth, actually allows you to do much better than the one without this intermediate representation. So here's an example. Now you have an input image, and this is what you get without modeling depth. And you can see that it's roughly capturing this weird chair, but it's not very close to the actual shape of the chair in the image. And this is what you get by modeling depths. You can see that by having depths at the intermediate representations, the reconstructions are much closer to what we want in input, as shown in input. And the depth map as intermediate representation, which we borrow from a top-down graphics engine, really allows the system to reconstruct more faithfully what the shape should be, and also to focus on what's important, that is the surface of the object, right? If you want to reconstruct a 3D shape, and what really matters is whether you can get the surface right. And having the depth as the intermediate representation really led the network to focus on the visible surface. And here is a different example. This is joint work with Yifan Wang, who is now a PhD student at University of Washington. He was an undergrad at MIT while I was a graduate student there. Okay, but at the beginning we said we care about generalizing to objects that we've never even seen before, right? But if you take these models and then you say, okay, now let's train it on 3 typical object classes: chairs, planes, and cars, and these are the 3 object classes that you can find the most CAD models for. So they're like, you can argue they're like the most common object categories. And then you test it on the table, which is also a very popular object class. You send the table image to neural networks, and this is what you get. You may want, okay, I want a table, but this doesn't look like a table. This looks much more like an airplane. Why is that? Because the neural networks doesn't have the ability to generalize to anything that it has never seen before during training. And I've only seen chairs, planes, and cars. Then I will say, okay, I'm now giving a new image that's a table. I don't know what it is, but the top of the table is round, and there are some airplanes that have similar shape. It's also round, looking from the angle. So I'll just retrieve a nearest neighbor from the training set, and that gives you an airplane. And this is not only a problem for our approach, but also a common problem for many other papers. And the problem of single image 3D reconstruction has become very popular in the past few years, where all those approaches using different representations like voxels, point clouds, meshes, multi-view images, and they all have this issue, that is they can't really generalize to new object classes. So how may we solve this problem? Right? Let's think more about what is the underlying physical model, what is the graphics engine behind the system. So let's look at the second part. The second part is shape computation network. Right now it takes a 2.5D depth map, right? And then output a 3D shape. So the depth map that we said, it's like a reparameterization of the visible surface. But essentially it's still a 2D image, right? It's still a 2D matrix, right? Like an image. And output is the 3D shape. So the network is implicitly learning the process of how we may project a 2D depth map, although it's a reparameterization of the visible surface. It's still a 2D image. How to reproject the depth map into 3D. But this process of 2D to 3D projection or back projection is a fully deterministic process and also fully differentiable, right? We learn it from geometry that our cameras, or how we can do 3D to 3D projection. And if this is something that we already know, and we can fully write it down, it's fully differentiable, then why are we asking the shape computation network to be so over-parameterized to learn such a deterministic mapping? Right? And this is universal, right? Every picture I see is 2D, and we know that every picture is capturing an underlying world that is 3D. So there's inherently a 3D to 2D projection and a 2D to 3D back projection problem. And it's so universal, it's so clear, but we're having a neural network relearning the thing. And the fact that you let it relearn, it learns only for the training classes. So instead of having a learning for the training classes, what if we just build it back into the system, write it as a differentiable layer? So now you have a system which first predict depth from the current image, and then do a differentiable but non-learnable back projection layer that takes the 2D depth map and back project it into the visible or partial surface in 3D. And then the second network can just focus on completion instead of focusing on back projection. It just take this partial surface, but now it's in 3D, and do shape completion in 3D. So now, if we take this model, which is trained on chairs, planes, and cars, and test it on the table, and this is what you get before direct prediction method, and this is what you get after modeling not only the intermediate representation, that is depth, but also the back projection model. Of course, it's not perfect. If you look at the surface of the table, you can see there are a lot of artifacts still, but it's really getting you much more interesting results, and also explains the image much better. It does look like a table. So this is joint work with Xiaomi and Jiajun, who are both PhD students at MIT. And here are a few more results where you train on chair springs and cars, but you test it on bookshelves and sofas. And compared with baselines, you can do much better and matches the ground truth better too. And here are more results where we try something that's even crazier. If we only train on rigid object classes like chair springs and cars, but now we test it on non-rigid objects. Here we're testing on human images and horse images. And would it work? And it's interesting that even if the model has only seen chair springs and cars, it does somehow generalize to humans and horses and give you a reasonable completion. Of course, if you compare with the ground truth, it's not as smooth as the ground truth, and there are a lot of artifacts. But it's interesting that the model does capture the fact that human has smooth surfaces and or objects or humans, but any shapes usually have a smooth surfaces that are complete and connected, and does give you a reasonable completion. Okay, so here we are saying how we may leverage the idea from a top-down model, a graphics engine, but use the intermediate representations like depth and back projection to build a system that not only works better but also generalizes to new classes. And we call our model generalizable reconstructor or genre. But if you look at the output of genre, and you feel like okay, it's pretty good, but if you look at the top of the table, right, it's not round as what we want. We have such a strong prior that objects are usually round, man-made objects are usually round, but genre doesn't have that. So I don't have time to talk about this in detail, but we also tried building in priors that humans have, that is, shapes often have abstract program-like structures, and can we go from shape reconstruction to shape abstraction, so that we designed a shape domain-specific language, which if you back project the shape, not only representing it in the voxel or any of the 3D representations, but representing it as a shape program, then the reconstruction is now able to capture the priors that humans have. Okay, so we spent a lot of time talking about this idea of learning to invert the physics model, especially the graphics engines. And let's also look at an example of how we may learn to augment it, how to make the graphics engines does even better. As we said before, a graphics engines you can take a shape and lightings and everything and render your picture. But what if I want to synthesize and render objects I've never seen before? So here we've leveraged the idea of generative adversarial networks, but not using it for 2D image generation, but for 3D shape generation, so that you can use scans to synthesize in novel 3D shapes. But you can also use the idea from computer graphics, that is how 3D to 3D projection works. So you can take the 3D shape, project it now forward in a forward direction, project it into a 2.5D depth map. And then you can have like a cyclogen or 2D texture network to add textures on top of the 3D shape, so that you can synthesize not only 3D shapes but also their corresponding 2D textures. You can also do shape and texture novel combinations. I have this synthesized the car, and then I have a picture of a car that I think is really beautiful. So I wonder how the car would look like if I took the texture from the image but put it on the shapes I synthesized. Right. So these kind of hybrid or augmented graphics engines that use depth and projections from graphics, but using neural networks for shape synthesis and texture synthesis also allows you to do new things. Okay, and finally, the idea of learning to invert and learning to augment can really be put together, right? So here's an example where if I'm given a picture of a car of an autonomous driving scene, I can first do the inverting graphics idea to get a representation of the scene with objects and their shapes and their positions and colors. And then I can say, what if I want to move the car to the right? So I can edit the scene representation, or imagine how the scene will look like. And then put it back into my augmented graphics engine pipeline to synthesize a new picture where everything else is the same, the weathers and shapes and everything, but the car has its position changed, now it's moving to the right. The idea of learning to meet physical models not only apply to graphics but also apply to physics. Right? A simple idea is I can given the block tower like this, I can first do inverse graphics to infer the positions and shapes of the blocks. And then I can directly send it into a dynamics model or a physics engine for prediction, and then back into a graphics engine for rendering to render what future pictures will look like. This is what we call in the learning to see physics. And given a picture like this, if you directly predict future pixels using neural network, you get something that's reasonable. If you compare with the ground truths, they're indeed pretty reasonable. But the output in long term are very blurry because it doesn't have a notion of objects. It doesn't know objects have geometry. But if you use our approach, then the inverse graphics, forward prediction, and forward rendering pipeline does give you reasonable predictions, but also pretty, I would say, sharp renderings. It also allows you to do other things, such as, given an input, if I reconstruct it, what if I have a wind or force coming from a certain direction? How would the scene look like? As well as if I have seen an image and I know in the future it's going to fall, then what are the stabilizing forces I can take to make the tower stable? Okay. But sometimes dynamics models can also be not enough. Right? For example, I have two objects like this. They have very similar visual appearance. But then I found, okay, if I've given them same external force, the outcomes are just very different. One tower falls and the other is roughly stable. Why is that? Because the objects have physical properties. Okay? The first one is made of aluminum, the second one is made of steel, so they just have very different physical properties. And also, if I'm pushing objects multiple times, like doing interactions, you found that even if I give it the same force from the same direction, the outcomes may be stochastic. So there's stochasticity in dynamics, which a typical physics engine may not do. So something I don't have time to talk about in detail, but we did also try it is to use learning to augment dynamics models, to make the simulations more accurate, to make simulations more stochastic, and eventually use it for robot manipulation. Right? Given a picture like this, if I want to go in from a single picture to reconstruct a tower, what do I have to know? I have to recognize different objects, blocks of different colors, different sizes and shapes. I have to understand physics so that if I want to rebuild a tower, I have to start from the bottom. If I start from the top, the thing will just fail. Right? So then I have to eventually use the inverse graphics and dynamics models, integrate them with the control algorithm for rebuilding the scene. So this is what we did. Just from a single image, inferring the objects and their attributes like shapes and colors, and understanding physics so that you rebuild the tower. And here are more results. It didn't success 100% of the time, but 7 out of 10 trials it was pretty successful. And eventually, we also tried extending the system to not only work with blocks, but also work with general objects like deformable objects and fluids by not only learning a dynamics models for rigid object interactions, but also learning a dynamics model for particle object interactions. So you can simulate, for example, this is from our model, the interaction of not only rigid bodies, but also the rigid bodies and fluids. And use it for eventually deploy on a robot for manipulating, for example, a piece of sushi. All right, so to summarize, our goal or the theme of my research is think about what data can really bring you and what a top-down generative and simulation engines can give you, especially in the context of a graphics engine and dynamics engines. And the key principle here is really to think about what's the causal structure, what's the core knowledge of the world that we can build in, and to think about how we may use learning to learn what the model doesn't give us. Thank you.